Section 12.3 is on trigonometric functions of general angles. Given theta, an angle in standard position, which I've marked here in pink, and point P, xy, a point on its terminal side, which is over here, the following things are true. R is the radius, okay, which if you were to complete the right triangle by drawing this vertical red line dashed here, you would have this leg is equal to x, this leg here is equal to y. R is the radius of a circle, which we'll take a look at in a minute, or the length of the hypotenuse. Then using the Pythagorean theorem, the length of r is the square root of x squared plus y squared. And the 6 trig functions of that angle are as follows. And this basically works off of SOHCAHTOA that we saw a couple sections ago. So in reference to this angle right here, y is the opposite, r is the hypotenuse, so y over r. Cosine, x is the adjacent, r is the hypotenuse, so it'd be x over r. For tangent, opposite over adjacent, y over x, and then cosecant, secant, and cotangent are the reciprocals of those. This is how we're going to find angles of the trig functions, find the values of the trig functions for angles that are greater than 90 degrees and less than 0. Let's take a look at an example here. This says the terminal side of theta in standard position contains the point -6, 2. Find the exact values of each of the 6 trig functions of theta. So in order to do this, I'm going to start with a little sketch. Because I'm a very visual person, I like to see what this looks like. So I have an angle, and I will go ahead and draw it here in blue, that contains the point, the terminal side contains the point -6, 2. So that's going to be right here. So my angle is going to look something like this. Okay, so that would be this angle right here. So I need to find what the exact values of the 6 trig functions are for that angle right there. Okay, well, looking at this, I know that my x is equal to -6, my y is equal to 2, and my radius, I'm going to do the square root of x squared plus y squared, which is the square root of 40, which simplifies to 2 square root of 10. Now remember, what this is referring to, I'll go ahead and draw it here in red, is if I were to draw this line right here, this is my y, this is my x, and this distance right here is my r. So I'm basically looking at a right triangle here. Okay, so sine of theta is going to be y over r, or 2 over 2 square root of 10, which simplifies to 1 over square root of 10, and rationalizing my denominator, is going to give me square root of 10 over 10. Cosine of theta is x over r, or -6 over 2 square root of 10, which gives me -3 over square root of 10, and rationalizing my denominator, -3 square root of 10 over 10. Tangent of theta is y over x, or 2 over -6, or a -1/3. Okay, that's using my SOHCAHTOA. Now let's do the reciprocals of those. So the reciprocal of sine is going to be cosecant. So cosecant of theta, and let's go ahead and flip that, and let's flip this one here, which is going to be square root of 10 over 1, or just square root of 10. The reciprocal of cosine is secant. And let's flip this one here, so that's going to give me a negative square root of 10 over 3, and cotangent of theta, the reciprocal of -1/3, or -3. Easiest way to do this type of problem is to draw a little bit of a sketch. A quadrantal angle is an angle in standard position whose terminal side lies on the x or the y axis. In other words, the angle is basically one quadrant of the coordinate plane. So here we have the blue line right here. So in this case, theta is equal to 0 degrees or 0 radians. Here we have theta is equal to 90 degrees or pi over 2 radians. And notice I'm marking the point here. So this would be the point r0 and this would be the point 0r. For this angle, pi is equal to 180 degrees or pi radians, gives me the point negative r0. And here theta is equal to 270 degrees or 3 pi over 2 radians, and that gives me the point 0, negative r. So let's do an example that's similar to this. This says the terminal side of theta in standard position contains the point negative 2, 0. Find the exact values of each of the 6 trig functions of theta. And what makes this a little tricky is we are going to have some zeros in here. So let's go ahead and draw a coordinate plane here. And my angle is going to have a point negative 2, 0, which is this point right here. So my angle goes from here over to here. I'll go ahead and draw the arc. So it's basically this angle here, and we need to find the 6 trig functions. So for this one, x is equal to negative 2, y is equal to 0, and in this case my r is equal to 2. That's basically that distance there. Okay, so sine of theta is y over r, which is 0. Cosine of theta is x over r, which is going to be negative 1. Tangent of theta is y over x, which is 0 over negative 2, which is 0. Cosecant of theta is going to be, instead of y over r over y, which gives me a 0. That is actually, 2 over 0, which is undefined. Secant of theta is going to be r over x, which is negative 1. And cotangent of theta is going to be x over y, which is negative 2 over 0, which is also undefined. So the point here is that when you're dealing with one of these quadrantal angles, you're going to have some values that are undefined, some that are 0, 1, or negative 1. If theta is a non-quadrantal angle in standard position, its reference angle, which we call theta prime, is the acute angle that is formed by the terminal side of theta and the x-axis. So for example, here in quadrant 1, here I have an angle, okay, in pink, theta, and theta prime, its reference angle is going to be the same because it's formed by the terminal side, which is the blue line, and the x-axis, so theta and theta prime are the same. In quadrant 2 over here, I have my angle theta in pink. Its reference angle is theta prime in green, okay, because it's formed by the terminal side, which is the blue line, and in this case the negative x-axis. Okay, theta prime is equal to 180 degrees minus theta, or in radians pi minus theta. And here in quadrant 3, I have my angle theta in pink, and my reference angle theta prime is this green angle right here, which is found by doing theta minus 180 degrees or theta minus pi. And in quadrant 4, my reference angle is right here, theta prime in green, which is 360 degrees minus theta, or 2 pi minus theta. Personally, I don't worry about memorizing these little formulas down here. I do a little sketch and look at it. Remember, the reference angle is formed by the terminal or the ending side of the angle and the x-axis. So just draw your angle and then look to see how do I need to go to get to the x-axis. So let's do a couple examples here. This says sketch each angle and then find its reference angle. So my first one is a negative 110 degrees. So let's go ahead and just do a little sketch of that. Okay, I'm going to go ahead and draw it in pink, I think. So here's my initial side, the positive x-axis. And since it's negative, I'm going to be going clockwise, and I need to go 110 degrees. So I'm going to go 90 degrees to here, and then I'll need to go a little bit more, basically another 20 degrees to get my angle. Okay, so that's a negative 110 degrees. So this angle right here was 20 degrees because I had to go 90 plus another 20. Now my reference angle is actually going to be this angle right here, which is going to be 90 minus 20, or 70 degrees. That's my theta prime. Okay, so in this case my reference angle is 70 degrees. Okay, example number 2 is 2 pi over 3. So this is written in radians, which, to be honest, for me it's a little easier if I convert it into degrees, and then I'll convert it back into radians for my final answer. So 2 pi over 3, let's multiply that by 180 over pi so that my pi's will cancel out, and that's going to give me 120 degrees. So to draw that angle, my initial side is here, the positive x-axis, and I'm going to go around 90 plus another 30 to give me 120 degrees. Okay, now this right here is going to be my reference angle. So since this was 30 degrees, I'll go ahead and do it in blue here. This was 90 plus 30, okay? That means that my theta prime, or my reference angle, is going to be 60 degrees, because 60 plus 30 gives me that 90 degree angle. Okay, so 60 degrees, but since my problem started in radians, it needs to end in radians, so I'm going to do 60 degrees times, I need to have a pi in my answer, pi over 180, or pi over 3. So in this case, my reference angle is pi over 3. Okay, here's a chart from your textbook that probably is about a good time to memorize this. Okay, the trigonometric values for our special angles. And remember, we had in geometry, we had 30, 60, 90 right triangles and 45, 45, 90 right triangles. 30, 45, and 60 are going to come up a lot. Actually, you probably only need to focus on the first 3 columns, sine, cosine, and tangent of a 30, 45, and 60 degree angle. Now, how do we get these? It's related to this little beastie called the unit circle. Okay, and you'll see that a lot of those same numbers that were over here, in fact, let's take a look at the numbers. So we have 1/2 square root of 2 over 2, square root of 3 over 2, and it kind of seems like all of the numbers. Okay, so for tangent it's a little different, but basically our sine and cosine and tangent, there's a lot of square roots of 3, square roots of 2, 1/2, that sort of thing. All of that comes from this here, the unit circle. So this is basically a circle that has a radius of 1 unit, and I know that because this point right here is 1, 0. Okay, and you'll notice I go up 1 unit up on the positive y-axis, and 1 unit this way and 1 unit this way. So the unit circle radius equals 1. Okay, so then they have all of these special angles marked out, our 30s, 45, 60, 90, and then we have 90 plus 30, 90 plus 45, 90 plus 60, and then another 90, and so on, going all the way around. And we have our radians that have all of those lovely pi's in them. But how did they come up with these crazy points out here? So how do I know that this point on the circle is exactly square root of 3 over 2, comma, 1/2? Well, that's related to the fact that this is 30 degree angle. If I were to draw this right here, so that's a 30 degree angle. Okay, now if I were to take and to drop this down to the x-axis and actually draw this over perpendicular to the y-axis, okay, this distance right here from the center to this point right here is actually square root of 3 over 2 units. That's where we get this x value from. This distance right here is square root of 3 over 2, and this distance right here on the y-axis is 1/2 of a unit. So that's how we get that point right there. Another interesting thing, so this means, it's kind of crowded in here, so this is square root of 3 over 2. This distance here is 1/2. Now if you want to look at this in terms of a triangle, the sine of an angle is opposite over hypotenuse. So the opposite of this 30 degree angle is 1/2. The hypotenuse is 1, so the sine of a 30-degree angle is 1/2. Cosine is adjacent over hypotenuse. This distance right here is the adjacent side, that's square root of 3 over 2. My hypotenuse is 1, so the cosine of 30 is square root of 3 over 2. So this is how we get these points right here. So if you remember from what we did at the beginning of the lesson, the y was basically the y variable here. Y was similar to sine, or I should say, let me say it this way. So sine of theta was y over r. Well, if r is equal to 1, then sine is the y value. Cosine was equal to x over r. Well, if r is 1, cosine is equal to the x value. So cosine of 30 is 3 square root of 3 over 2. Sine of 30 is 1/2, and so on going around the circle. Now there's various ways to remember this. Actually, you don't have to memorize all these. There's little tricks to figure it out. We'll go over some of these in class. I also found some really great videos on YouTube about how to do this. So that's basically the unit circle. You'll see a whole lot more of it in pre-calc, and we'll talk about it a little bit in class. So let's take a look at our last couple examples here that say find the exact value of each trig function. So here I have cosine of 135 degrees. I could go back to my chart. I could cheat by looking at the unit circle, but I'm going to do a little sketch here. First thing I want to do is draw a 135-degree angle. So that's going to start here. Okay, and it's going to go around 90 plus another 45 to there. So that's my 135-degree angle. Notice that my reference angle right here is going to be 45 degrees. Okay, so that's my theta prime. Go ahead and label that. So basically I'm looking for the cosine of a 45-degree angle, which is square root of 2 over 2. But notice that's the x value. Cosine was the x, so, and in this quadrant x is negative, so the cosine of a 135-degree angle is going to be a negative square root of 2 over 2. Okay, let's do tangent of 5 pi over 6. Again, I'm going to draw a sketch. Okay, and 5 pi over 6. So remember, all the way around, from here all the way over, so that's pi over 2, but all the way around is pi, but I only need to go 5/6 of the way. So that's 5 pi over 6, or 5/6 of pi. Okay, so that means that down here, my reference angle, my theta prime, is going to be equal to pi over 6. And I need the tangent of that. Okay, so to get the tangent of that, I'm going to actually I'm going to put a point out here, and I know I'm kind of writing over what I have here. I'm going to complete my little triangle here, create a little right triangle by drawing lines, perpendicular lines to the x and y axes. Then I realize that this distance here is the longer of the two, so that's going to give me this point here of negative square root of 3 over 2, and it's going to give me this point here as 1/2. So tangent is y over x, so 1/2 over a negative square root of 3 over 2, which gives me a negative square root of 3 over 3. So in this lesson, we took a look at the trigonometric functions of general angles. And I know this video was a little bit long, but we covered a lot of information with regard to how to figure out the trig function of any angle given its point. Also how to deal with quadrantal angles, reference angles, which are very important. We took a look at the sine, cosine, and tangent of our special angles, 30, 45s, and 60s, and took a look at the unit circle.